We just got done talking about these block level protocols like iSCSI and fiber channel over Ethernet. In this video, we want to explore a little bit more detail of what that entails, and specifically around the idea of iSCSI and fiber channel. In the next video, then we'll take a look at fiber channel over Ethernet, which is its own conversation. Let's dive into these two protocols. So as we recall from our last video, we have a server that is now empty of disks. We don't have any kind of local storage. And so we're going to connect across some kind of network and attach to storage that's just sort of out there. And so what are we going to do and how are we going to do this? Well, first of all, we remember that we are connecting our CPUs to our storage via this SCSI protocol. And that's not going to change. We need these SCSI messages to make it across the network. And as it turns out, we have multiple ways to do that. The first of which we talked about is iSCSI. iSCSI is SCSI messages inside of a TCP/IP packet. This information is going to be carried inside of a payload. So really we have our SCSI messaging in here, and then we have our TCP header, and then we have our IP header. Now, in order to deploy iSCSI, we need at least 1 gig connections. Although we can go all the way up higher if needed. We can go all the way up to 100 gig. Deploying iSCSI across any one of these links is really just considered to be traffic on the link. The reason for 1 gig is because storage traffic can be data heavy. And so we need enough bandwidth in order to support the conversations that are happening between our servers and our storage. In fact, generally speaking, this network up here, it's got to be resilient. I've said before in previous skills, if you're working your way through the DCCOR course, that if this network were to go down for any reason, imagine if this server had this hard drive back inside of it and we simply reached in there and yanked out the cable that's between the CPU, I call it between the CPU and the storage. Really, it's between the storage and the motherboard. But either way, if I were to reach in there while the server is online and pull that cable out, what would happen? I can promise you nothing good. This server is going to have major problems. And so it's not going to look any different if we actually lose the networking in between the storage and the server, because that's effectively what we just did. We just reached down there and ripped it out. And so number one, we're going to need to make sure that this is a resilient network, and in some cases, that means 2 different connections in some way, and we'll get to that here in a little bit. However, we also want to make this efficient. So one of the ways we can make this efficient is by leveraging jumbo frames. Jumbo frames are designed to effectively increase the ratio between our data that's in the payload and the headers. So if I can increase my jumbo frames to be 9,000 bytes instead of a traditional Ethernet frame at 1,500 bytes, then in this case I go from 6 headers down to a single header. Since I have only 1 header, I actually recover 5 headers worth of bytes that I can now dedicate towards carrying SCSI messages. Now, the other option that we talked about in the last video, it's worth pointing out here again, is that from a resiliency perspective, it can be a little bit risky running iSCSI on our traditional network. Because let's imagine a scenario where my server is connected to my storage array through the traditional network, except this is where also the users live. Well, we know that problems develop on the user networks, and we might actually end up with a network loop, or just a lot of contention on the network. And if we have a lot of contention, then we might actually drop iSCSI packets. Well, the biggest problem with iSCSI, and the biggest thing we need to worry about, is dropped packets. The TCP/IP network, it's great that we're running this on TCP because it gives us reliability, but every time I have to send a packet and then realize, oh, that got dropped, and then send it again, well, that's going to cause major slowness on my storage network, and that can cause all of my applications in my data center to slow down. And so oftentimes, instead of deploying the storage network onto the user side of the network, we will deploy a dedicated iSCSI storage network. Now, depending on what you have set up in your environment, you might look at this and say, no, we are running on the traditional infrastructure, and that's fine. We can make this work, but understand the risks and understand what we should be doing. In other words, jumbo frames and as much bandwidth as possible, then we should be good to go. But at the same time, deploying a dedicated set of network switches that only handle iSCSI traffic through different NICs on the servers, oh, that's another great way to go. So iSCSI was one option for carrying these SCSI messages. Another one would be fiber channel. And in a lot of cases, our European friends will be happy, we spell fiber channel like F-I-B-R-E, like we do across the pond. Me being in the US, my English says to spell fiber F-I-B-E-R. However, in order to distinguish between fiber optics, which we often use the American spelling for, we tend to use the European spelling. And so we don't want to get confused between these two concepts. So all that to say, fiber channel, which can be abbreviated as FC, we can think of it as if it's its own set of layer 2 and layer 3 protocols, all wrapped up into one. And because it's a layer 2 protocol, it's not going to get along so well with Ethernet. In the last video, I said that fiber channel and Ethernet are like oil and water, and that's because I can't plug a fiber channel device into an upstream Ethernet device and expect this just to natively work. This isn't an option, although there is this concept of fiber channel over Ethernet, which again, is a big enough subject that we're going to talk about in a dedicated video up next. So because these require their own dedicated switches, Cisco actually has a completely different line of switches, their fiber channel switches, and these are known as MDS. Typically, these are MDS 9000s, we call them. So we've got, for example, the 9100s, which are like top-of-rack switches. We also have the 9500s, which are chassis versions. And so we have a lot of different options in the MDS line, and we'll be going into those in more detail in Domain 3 of the DCCOR course. Now, just like iSCSI, the purpose of this is to encapsulate our SCSI messages into a frame that's going to carry it across the network. Now, because Fiber Channel is essentially its own stack of protocols, we are going to place the Fiber Channel header in front of the iSCSI messaging, and that is our entire packet. And this is traditionally 2,112 bytes in size. Now, if you've heard one thing about Fiber Channel switching in the past, it might be that it uses this crazy lossless technology. When I say crazy, I'm really referring to the fact that I'm a TCP/IP, a traditional networking engineer. The idea of a lossless network, it makes me scratch my head, because that's just something I don't understand swimming in the world of Ethernet all these years. Because I know that if I've got two Ethernet switches, and this Ethernet switch down here, this is just completely overloaded, this switch up here, it's just going to keep sending traffic down. And that traffic might land on an interface where we don't have enough buffer space for it, and a lot of these packets might get dropped. This is why we run TCP. TCP gives us reliability. It will resend the frame if it gets dropped. And in some cases, we use applications where the drops don't matter, in which case we'd use UDP. It's less reliable, but boy is it faster. Well, none of these concepts actually exist inside the Fiber Channel space. We will never overload a buffer on a Fiber Channel switch, and the reason for that is because when we have two Fiber Channel switches now communicating with one another, this Fiber Channel switch up top will tell the bottom Fiber Channel switch how many buffer-to-buffer credits that it gets. The buffer-to-buffer credit tells it essentially how many packets that it's able to send. Let's use an example of 16. So when I send a packet upstream, I decrement my counter down to 15. Then when an acknowledgement comes back, I actually get to increase my credit back to 16. So worst case scenario, I send 16 consecutive packets and that upstream Fiber Channel switch is so busy, I never get an acknowledgement back. Well, once my credit limit goes down to 0, I stop sending frames. I am no longer going to send traffic to that upstream Fiber Channel switch because I know that it can't handle it. And so this is why our frames get as lossless as possible. Because we're no longer overloading buffers, we should never see an intentionally dropped packet in the Fiber Channel network. Now, if you've heard one other thing about Fiber Channel, it might be this concept of distinct fabrics. When we're talking about the concept of a fabric, usually from a networking perspective, we might as well think of it as distinct networks. But we're talking about very distinct networks. We're talking about this concept of an air-gapped network. What do I mean by that? Well, what I mean is separate physical switches that are in no way communicating with one another. So I might have 4 switches here, 1, 2, 3, and 4, and I connect switches 1 and 2 together and 3 and 4 together. Now down here, I can have a server that connects up to these 2 different paths. I can have storage up here that connects into these 2 different paths. And this network over here, this is known as Fabric A, and the fabric over here is known as Fabric B. And you'll notice that Fabric A switches do not communicate and directly attach to Fabric B switches and vice versa. Instead, my servers have access to both fabrics, my storage has access to both fabrics, and therefore I have 2 completely redundant paths through this network. The reason for this comes back to that concept of resiliency. The more resilient my Fiber Channel storage area network is, then the more likely I am to never see a major problem with communicating between servers and storage. We want to prevent this scenario on the left from happening. If a fabric were to go down for any reason, I've got a different path to my storage. Now, the last thing I want to talk about with Fiber Channel is the concept of connectivity. Because we are used to, generally speaking, connectivity on a TCP/IP network. I understand that an Ethernet adapter is known as a NIC, and that NIC has a MAC address. That all is something that, as a network engineer, I've spent a lot of time studying. But did you know that in the Fiber Channel space, we also have an adapter? We call it the host bus adapter, otherwise known as an HBA. Furthermore, the HBA is going to have a worldwide name on it. And actually, there are 2 different types of worldwide names that are burned into an HBA. We have a worldwide node name that would apply to the HBA itself, but then that HBA might have 2 separate ports on it. And each one of those ports would get a worldwide port name. We have WWNNs and we have WWPNs in the Fiber Channel space. So back up to this drawing here, this server is going to have an HBA here and an HBA here, or possibly it's one HBA with 2 different ports on it. Either way, that is how we connect into the Fiber Channel world. Just like we have NICs and MAC addresses on the Ethernet side, we have host bus adapters and worldwide names on the Fiber Channel side. Now, one last thing to discuss in all of this, and it might be a question on your mind, is what does this actually physically look like? Well, as the name fiber channel implies, it's going to rely on fiber optics. Specifically, it's going to use LC connector types in an SFP form factor. Just like with Ethernet optics, we have long-range options and we have short-range options. And furthermore, we need to select our speed types. Unlike Ethernet, we have factors of 2 in our speeds. So for example, back in the day, we had 1, 2, and 4 gig fiber channel, but these days, we're probably going to see 8 gig at a minimum, but also so we can see 16 and 32 and even 64 gig is on the horizon, at least at the time of this video. It might already be out by the time you're watching this. Now the question you might be asking yourself is, okay, so these are SFP connector types, which means I can physically connect them into any SFP port, but can I do that? Can I just plug them into any Ethernet SFP interface? And the answer is no. We need a special type of interface known as a unified port if we're going to be able to plug these into traditional Ethernet interfaces. However, if we were to get the MDS switches, which are Cisco's fiber channel switches, we would see that it's a bunch of SFP interfaces on these particular switch types. So whether we're plugging directly into a native fiber channel port or we're connecting via a unified port, either way, we can expect to see fiber and LC types in an SFP form factor. So as we see here, we have two different options for getting our SCSI messages across some kind of network. The first of which is iSCSI. iSCSI is great because it leverages TCP/IP. We can send it across our existing networks. Or, by the way, we might opt to deploy a dedicated set of switches to make our iSCSI environment more resilient and free from contention. Now, fiber channel, it's its own protocol. It's a whole set of information that we're going to have to learn over the course of the DCCOR course. Now, what at least we can understand from this conversation is that fiber channel is going to require its own set of switches, so we can't simply send fiber channel traffic across a 3850 or 6500, a traditional Catalyst Ethernet switch. And furthermore, fiber channel is going to make us all scratch our heads because we're Ethernet engineers, we're used to loss. Fiber channel is lossless. It's a lossless protocol. We use those buffer-to-buffer credits to ensure that we never overrun a buffer, and we form our connections using those host bus adapters and worldwide names. I hope this has been informative for you, and I'd like to thank you for viewing.